Sasha will try to adapt. Okay, so Sasha, thank you very much for the introduction, and thank you everybody for coming on such a wonderful Saturday morning to this lecture. I will talk about approximation algorithms and semi-definite programming, and I'm sure all of you have slightly different background in theory and in algorithms, so I'll try to adapt my topics depending on your interests as well and based on your background. So my plan is first to do some basic introduction to approximation algorithms, just to show you some sort of toy examples, and afterwards talk about more advanced topics on linear programming and, as promised in the title, on semi-definite programming. So I will speak English because this is probably the language of this CSEDays. But feel free to ask questions in Russian as well. And I hope that this lecture will be very interactive. So feel free to interrupt me at any point of time and ask questions, especially when I give definitions, because I think if you don't understand definition, you probably won't understand the talk itself. And let's start with maybe a very basic approximation combinatorial optimization problem. And the problems that I had to solve when I went to this conference. So I live now in Seattle in the United States, and I need to go to Yekaterinburg, somewhere here. But on this trip, I wanted as well to visit Moscow, my family there. And then I want to go to maybe Riga for ICALP conference. And that's about it. But in theory, I maybe could visit some other cities, San Francisco, let's say, and New York, and whatever, Paris. And now this doesn't look like a map at all, but so I have some destinations I want to visit. And so the question, in which order I need to visit these cities to minimize my travel time. And maybe in this case, the minimum tour looks like this. But if I had more cities, the problem would become very hard. And of course, for my travel, I had some constraints. I had to be at Yekaterinburg today, and maybe I need to be in Riga next week because ICALP will be next week there. This problem is very relevant. So the problem is called travel salesperson problem, or TSP. And this problem is actually very relevant in practice as well. So for practitioners, if you have some FedEx or DHL or UPS postal company, they need to deliver some goods to different clients, some packages to different clients, and they want to minimize the tour. So in other words, in this problem, we have a graph G, and we have distances between the vertices of this graph. So some metric space. And our goal is to find a tour, some path visiting all vertices V0, V1, etc. and coming back. And we want to minimize the length of this path. So probably many people in this audience are familiar with this problem. And this problem is hard, at least in theory. It is NP hard, so we can't really hope to find an exact algorithm for the problem. So let's see what we can do. So what kind of approximation algorithms are possible? So what is an approximation algorithm? We want to design some algorithm or heuristic that finds a solution to this problem, but we don't require that the solution is necessarily optimal solution, the exact optimal solution, but we want to have some approximation guarantees. So if the optimal value, let's denote it by opt, as it's usually done, and the cost of the solution found by the algorithm is alg, then we want that the cost of the algorithm is less than some alpha times the cost of the optimal solution. And we want to design an algorithm with a provable guarantee. So we want alpha, the approximation ratio of the algorithm, to be as small as possible. The most basic algorithm for this problem, any questions about the problem formulation, by the way, is as follows. So let's look at the optimal path in our graph. And let's remove one of the edges from the path. In this case, we get a tree, right? We have a path, and we remove one edge. Sorry, we have a cycle, we remove one edge, we get a path, and that path is also a tree. Maybe instead of looking for the optimal tour, TSP tour, we can find a minimum spanning tree. So a minimum spanning tree is a tree that spans all the vertices in the graph and whose sum of lengths of edges is minimal. And this problem is easier. So we can find a tree with the minimum sum of edges. So let T be MST. And it's clear that the cost of the tree which is just the sum of length of edges, sort of we sum up over all edges belonging to the tree and their length, sort of length of this edge E. This value is less than the cost of the optimal solution, right? Because the optimal solution to the original problem, to the MST problem, is some cycle. If we remove one edge, we get a path, and the path is also a tree. So, of course, once we get a tree, it's very far away from what we really want to find. So we find the tree can be a rather complicated object, something like this, let's say. And so how do we construct a tour from the tree? And the most obvious way is just to do some kind of depth first search. So what we'll do, we'll go along every edge twice. So our solution is going to be something like this. So sometimes we will return to vertices previously visited, but what's important that we will visit all vertices at least once, right? We can also, so the distances in this graph satisfy triangle inequality. So instead of going back to some vertex, we can make a shortcut. For example, with this vertex, let's say this vertex, we don't have to go back to this vertex, but we can do a shortcut and go only to those vertices not yet visited. But that's not important. So the most important thing that we can go along the edges of this tree, go along every edge one way and then the other way, so that we will traverse every edge only twice and visit all the vertices of the graph, all the cities sort of in this TSP problem. So what's the cost of the solution we get? So the cost of the algorithm is at most twice the cost of this tree, right? Because we went over every edge twice. And we know that the cost of this tree is at most opt. So 2 costs is bounded by 2 opt. And this way we got 2 approximation. So this algorithm returns a solution that's always is at most 2 times worse than the optimal solution to the original problem. So of course we want to do better than 2, and so can we do that? And turns out that yes, we can. So the algorithm I just presented is very simple. We consider just slightly more complex algorithm, which is called CSEDays algorithm from mid-70s. And the idea is the following. So instead of going back, so we will try to so we will change our tree a little bit so that all degrees of the graph of sort of our tree plus some extra edges are even. So maybe let's start with some examples. So for example, if our tree just a path, then what the algorithm I described would do, it would go from the one vertex root of that tree all the way to the last vertex. So this is V0 to Vn, and then go back along the same set of edges. And of course, it's a waste of our time, because instead we could go from the last vertex to the first vertex directly, and that would be much cheaper. So essentially, what we want to do, we want to go every time from our vertex of the tree to some other vertex that we haven't yet visited. And this is possible if all degrees in this tree are even, right? Because in this case, the graph is Eulerian, and we can go along, we can traverse this graph by visiting, by going along all edges of the graph exactly once. And to make...
What do you mean all there are tree, there are leaves?
Right, there are leaves. So we need to kind of tweak this graph in some way. So we have this tree, and we will convert it to a different graph. So this is a tree, and we will convert it to some graph H. And to do so, we will identify all vertices of what degree, and particularly all leaves, right? Because from leaves all leaves have degree 1, and from those leaves we can't really go anywhere else. So let's see. In this example, actually, all vertices of what degree are these vertices, because the other two have degree 4, but in general, we could have maybe something like this as well. So the picture could be like this, and then, of course, this vertex and this vertex would also have odd degrees. So we identify all such vertices, and then we find a perfect matching of minimum cost among these identified vertices. So red vertices in my picture. Okay? So we find this a perfect matching. Okay, yeah, something like this. And we add this new matching to our graph.
That's a matching.
Something wrong with this.
Yeah, something is wrong, yeah.
As the intermediate vertex is not matched. And one is matched twice.
Which one is matched twice?
Left down.
Right, okay. Yeah, good. So maybe something like this. So, and we'll add H to be T plus M, where M is this minimum matching among red vertices. In the new graph, all degrees, of course, have an even degree, right? Because some vertices already had even degrees, and some vertices previously had an odd degree, but we appended them with an extra h, so the degree is now even. So the new graph h is Eulerian, and there is a tour in this graph that goes along every edge exactly once and visits all the vertices of the graph. And this is our solution. So this is the solution we are going to output. And so what's the cost of this solution? So the cost of our solution equals to the cost of the tree plus the cost of the matching. And we know how to bound the cost of the tree already. So it's bounded by the cost of the optimal solution to our original TSP problem. So now the question is how to bound the cost of the matching. And so we have these red vertices, right? And if you look at the original TSP tour, the original TSP tour visits all the vertices in the graph. And particularly since we are looking at the metric space on our graph, so all distances satisfy triangle inequalities, and because of this, so the original tour may look like this. So we have some blue vertices and some maybe red vertices. And there is a TSP tour. If we do shortcuts and ignore blue vertices, go directly from one red vertex to the next red vertex on our tour, we can only save the distance, right? Because all distances satisfy a triangle inequality. So there is a tour visiting only red vertices with length less than or equal to the original length of the optimal solution. And now this tour can be split into parts. So we can look at even edges on this tour and odd edges. Both of these form a matching. So it means that there are two matchings among red vertices, M1 and M2. And so that the cost of these two matchings, that that can be constructed from the optimal solution. Again, we don't know the optimal solution, but we do know that such two matchings exist, M1 and M2, and we know that the cost of M1 plus the cost of M2 is less than the cost of the original optimal solution, and particularly it means that for some matching, the cost of that matching is less than opt over 2. So there is a matching of cost half of the optimal solution. And now we are ready to bound the cost of our approximation algorithm, so the cost of the algorithm is less than 3/2 of the optimal solution. Okay? Any questions so far? This algorithm was invented in mid-70s, and so far this is a best-known algorithm for the problem. So in some special cases, we know that this 3/2 can be improved, but this is a big open question whether we can do better in the worst case. Maybe as a side note, I'll mention that sort of similar techniques actually are also used in practice in some sense, meaning that linear program, which is similar to this, is used in practice together with some other techniques like branch and bound techniques. Other, of course, in practice, other techniques like local search as well are used. And theoretically, if all our cities are on a plane or in some high-dimensional space, maybe low-dimensional space, we can do better. So we can find almost exact solutions. Those algorithms are quite theoretical, but in practice this problem is not very hard either, so we can usually find a solution which is within maybe 3% of the optimal solution. But for a general metric space, this is a big question whether this bound can be improved. And now maybe let me switch to another problem. Any questions? Which is called set cover. And I will show you yet another combinatorial algorithm, combinatorial optimization algorithm. So in this problem, they have some domain of size, let's say n, domain V of size n. And we have a family of sets covering vertices, these elements, let's call them vertices, in our domain. So F is a family of sets. We know that every element in our domain is covered by at least one set S. So the union of all sets in our family cover everything in the domain. And the question is, we want to find minimum number of sets in our family such that sets in this subfamily also cover all vertices in our domain. And for this problem, I'll present maybe two algorithms illustrating different ideas. And the more, so sort of this problem is good that pretty much any algorithm gives the same approximation for the problem. And of course, the most, maybe one of the most natural algorithms for this problem is just a greedy algorithm. So the algorithm will work as follows. So it will work in stages, sort of in steps. So let's say that V0 is our original set V. And then let's do the following. So while there are some uncovered vertices, so V sub t will be the set of uncovered vertices. While it's not empty, let's do the following. We will non-empty, right? Okay, good. So let's pick some set in our family such that covers most uncovered yet vertices, right? So that maximizes the number of yet uncovered vertices. So the intersection of this set S and the set of uncovered vertices is the maximum. And we pick the set, so we output the set. So let's say this is set S sub t. We will output, and we will cover all vertices, of course, covered by the set. So Vt plus 1 equals to Vt minus S sub t. So this is pretty much the algorithm. And finally, output. Here.
No, that's not. There are U and V which are indistinguishable on the blackboard.
What's that?
There are some letters which are similar U and some are V.
No, all of these are V's. They're not indistinguishable, these are the same letter. There is S, V, and S. Sorry, S and V, right? There is no U.
What is V0 is equal to what? Oh, it's
V. This is the original set. Right, and so V0 is the set of original vertices, and then sort of. So again, what we do, we start with all our vertices that are uncovered. Then at every step, we pick a set from our family that covers most of a sort of maximum possible, the maximum among all sets S of yet uncovered vertices. So at the first step, particularly, we take just the largest set. It is possible that there are several largest sets, and we pick just one of them, so we don't care which one. Maybe in some pre-specified order. So once we pick that set and covered some vertices, we change our set of uncovered vertices accordingly, and we just recurse. So we iterate this process, and we output this set V0 to S sub t. So let's see how good is this algorithm. Let's say that K, let's denote by the K actually the cost of the optimal solution. So we know that there exists some family of sets of size at most, actually exactly K, that cover all vertices in V. So the question, can we prove anything about this T? So T is, the algorithm returns T sets. Let's see. How good is it? To do so, let's look how these sets Vt change. I want to keep the algorithm on the board, so maybe I'll do something in here. So we have sort of our domain, our universe V. And at a certain point, at step t, we already have sort of some vertices already covered, maybe these vertices, and this is V sub t, the set of yet uncovered vertices. We do know that there exists an optimal solution. We don't actually know what it is, but it does exist. And so it somehow splits our set in k pieces. So this k pieces may overlap. And so it splits the whole set, but particularly it splits the set V sub t in k pieces as well, right? So we just look at the restriction to Vt, and the optimal solution also splits this set in k pieces as well. So because of this, there exists some S in the optimal solution. There exists some S such that S covers at least 1/k fraction of the set V sub t. So S intersected with Vt is at least 1/k fraction of Vt. So our algorithm, of course, finds some possibly other set S. But we know that for the set S our algorithm finds, this intersection can only be larger than this one. So if you look at the set our algorithm finds, which may or may not be the same S, its intersection is greater than or equal to the intersection of S with Vt and greater than 1/k times Vt. Okay? So now what we have is that now we can bound how quickly the set V sub t decreases. So the size of the set Vt plus 1 is less than the original size Vt minus the number of vertices removed, which is at least 1/k fraction of the set Vt, right? So this is 1 minus 1/k times Vt. And so what we get using this recursive relation is that the size of the set Vt is less than 1 minus 1/k to the power of t times the original set V0, right? And the original size of the set is just because we define, by definition, has size n. So n denotes the size of the domain. So it's 1 minus 1/k to the power of t. And particularly if we look at t equal k log n, we'll get that 1 minus 1/k to the t, which is 1 minus 1/k to the k, 2 log n, so this is 1/e, we can bound it. So this is less than 1/n. So in k,
This is the nature of it.
yeah, it's natural language. So in k log n steps, the set Vt will shrink to 1 or maybe less than 1 vertex. And then, of course, just one set covers that one vertex. So this is the bound we get. So we know that the number of iterations, so the number of iterations is less than or equal to k log n, maybe plus 1 or something like that. We need to be a little bit careful with rounding. And again, k was the number of sets in the optimal solution. So this is optimal solutions times log n.
Something is strange actually. So if we
No, we can cover everything except one of the one by k sets.
We'll cover a constant fraction of all sets.
No, this is fraction.
Or maybe.
Oh, yeah.
Okay,
right,
okay.
right, right.
Okay, let's be. So this is a fraction of. So this one, right? This is a fraction of covered vertices. Right. So the number of vertices, this quantity times n. Right. Very good. So.
And actually to be completely straight.
So from this. Yeah, so maybe we need one extra set, or we should be careful with this rounding up, down. So let me write +1 just. Okay, and so when is the first? It's 15 minutes. I have more. The 10 minutes.
I think it is the 10 minutes algorithm.
Any questions about this? And so let me now give you a different algorithm for the same problem and sort of introduce maybe a new technique. So maybe let's talk about linear programming. One way, suppose we have an optimal solution f prime. Let's now introduce indicator variable x sub I. So x sub s for every set in our family S. So x sub s is going to be equal to 1 if, so sort of let's say f prime is the optimal solution for now. 1 if S belongs to the optimal solution. And 0 if S doesn't belong to the optimal solution. So it belongs to the complement. Now, we know that, so what's the cost of the solution? Of the optimal solution, or opt? It is equal just to the summation of all x sub s's over all sets S in the family, right? So because we get here exactly, so we get 1 for in the sum, 1 for every S belonging to our family. And we know that every vertex in the domain is covered with at least one set. And this condition can be rewritten as follows. So if for every element I in our domain, if the sum over all sets that contain this element, sort of all sets in our original family of sets, then there exists one set that belongs to the optimal solution, right? So x sub s greater than 1. So this is a condition.
Just to make the unlivable sum, we should make that prime, not s in. No,
No, actually, I want it to be this f, right? So I get 0 if s. So the definition, if I define x sub s to be sort of the indicator, right? It's 1 for. Okay, good. So x sub s is the indicator of this event that s belongs to the optimal solution. So it's 1 if s belongs to the optimal solution and 0 otherwise. And so the first sum equals exactly to the number of sets belonging to the optimal solution. And the second sum for every I is the number of sets that cover that vertex I. And it can be more than 1. So we can't guarantee that it is exactly 1 in the optimal solution, but it is at least 1. So finally, we know that all these XS sub S belong to the set 0, 1. And this is called an integer program for this optimization problem. And in fact, so integer programming is really commonly used in practice. So this is interesting maybe for those of you who are interested in practical applications. And there are ways to solve many integral programs efficiently. So essentially, this formulation, so if we denote x sub s to be like this, 1 if s belongs to f prime and 0 otherwise, we get some integral solution. So we get some, for every set, a value either 0 or 1, right, this variable xs. But we can go the other way around. So we can write this optimization problem, sort of, and forget that, sort of, this optimization problem, and forget how we got x sub s's. And if we manage to find the optimal solution, optimal assignment of 0 and 1s to x sub s's, satisfying this constraint, then we will get the optimal solution to our original problem. And so how we get it, if x sub s equal to 1, so we'll do it, so x sub s if it is
Indicator or coefficient?
Huh?
The x sub s is the indicator function.
Indicator function, yeah.
But then what do you mean by 0, 1? It's coefficient is 0, 1.
No. Suppose we can solve this problem, right? This is this integral problem. Suppose, now let's look at this problem in this frame, right? So we can get some values x sub s. So s has sets. So all these variables are indexed by the sets. And suppose we can solve it somehow. Find the minimum. Okay, sorry. So the problem is now like this. Let me clarify. So we want really to minimize this quantity. Minimize this quantity. Sum of x sub s. Satisfying the constraint, the second constraint, sort of the second line here, that for every I in the domain, sum of x sub s's, where s contains I, is greater than or equal to 1. And suppose we put this constraint that xs is either 0 and 1. So let's say we can solve this problem. Then we are in a very good shape because we can reconstruct the optimal solution to the problem as well. So what we do, if for some x sub s, if some x sub s equal to 1, sort of in the optimal solution, let's denote by x star s the optimal solution to this integer program, then we will output s. So s belongs to the solution we want. So s belongs to some solution. And if x sub s, the optimal solution, equals to 0, then s doesn't belong. So that's what we'll do. And it's easy to see that the solution constructed in such a way from a solution of the integral program, right, from this x sub s's, is a valid solution for our vertex cover. So there is one-to-one correspondence between the solution to the set cover problem and solution to this integer program, right? So now the question is how to solve this integer program. And there are various methods, again, in practice to do it, particularly various variants of branch and bound techniques. But for our purpose, so the problem is as hard as the original problem. So we didn't gain so far anything by writing the problem in this way, but now we have more flexibility and we can sort of relax this problem. So let's replace this condition that every x sub s belongs to 0, 1 with the condition that every x sub s belongs to the interval from the 0 to 1. And once we do it, we get what's called a linear program. So this is a linear program, and there are various methods that solve this problem very quickly, and particularly in polynomial time. Okay? Questions?
What is f double x? What? F double x?
Right, so let's, this is a set returned by algorithm. Okay, so what I mean is that, let's see, maybe let me clarify. So for the integral program, we know that the cost of this integral program, let's say integer program IP, is at most the cost of the optimal solution, right? Because if I have that optimal solution, we can always construct the corresponding set of x sub s's. So xs is just the indicator whether s belongs to the integral solution or not. But we can go the other way around. So if we do have a solution to the integral problem, and we have every xs being 0 or 1, then we will define our new solutions, let's say f2 primes. So s is going to belong to that solution f2 primes if x sub s equal to 1, and it won't belong to f2 primes if x sub s equal to 0. And it's easy to verify that this is a really valid solution to the set cover from this constraint, right? From this constraint, we get that there exists one S covering each vertex. So for every I in the domain, there at least exists one S for which x sub s is greater than 1, and the corresponding S covers the set I in our solution as f2 primes. And of course, the number of sets in our solution exactly equals to this sum. So we get another inequality that opt is less than equal to the cost of the integral program, which implies that they cost just the same. Okay? More questions? Once we, but now we rewrite this solution as a linear program, and we relax this condition that x sub s now doesn't have to be either 0 or 1, but it rather lies in the interval from 0 and 1. And of course, any original solution to the problem, any integral solution, is also a solution to our linear program. So the cost of the solution can only decrease. So the LP value, let's denote by LP, is less than the cost of the sort of this integral value, which is the same as the optimal solution. And unfortunately, this cost may be much less than the cost of the optimal solution. So we really want it to be a very good approximation to the original cost, but it may be much less. And maybe it's a good time to make a break. So short, I guess, short break now.